conductors in question are not service entrance conductors, as they are connected to the secondary side of a transformer. However, they are supplying a main distribution board and are therefore feeders. Article 240.21b6 allows for a transformer tap of up to 25 feet in length to be exempted from overcurrent protection at the source. This is intended for short runs to motors or other loads where overcurrent protection is provided by the device being fed. In this case, the conductors run to a main distribution board, not a specific load. Therefore, the exemption in Article 240.21b6 does not apply. Article 230.7 requires that feeders be protected from overcurrent at their source. Since the conductors in question do not have overcurrent protection at their source, which is the transformer secondary, they are in violation of this article. The contractor may argue that the conductors are separated from other cables in pole boxes and wireway, which provides sufficient protection from physical damage. While pole boxes and wireway provide some degree of physical protection, they do not provide the same level of protection as overcurrent devices. Overcurrent devices are designed to prevent conductors from overheating, which can lead to fires. The installation is a violation of Article 230.7 because the secondary conductors from the transformer to the main distribution board are not protected from overcurrent at their source. Recommendations include installing overcurrent protection devices at the source of the secondary conductors and routing the secondary conductors to provide 6 inches of separation from other cables in the junction boxes. Now, let's delve deeper into the specifics of Article 230.7 and 240.21b6 to fully understand the implications. Article 230.7, titled Overcurrent Protection of Service Entrance Conductors and Feeders, mandates that all service entrance conductors and feeders be protected against overcurrent. Overcurrent, in this context, refers to any current in excess of the rated ampacity of the conductors. This protection is typically provided by fuses or circuit breakers. The primary purpose of overcurrent protection is to prevent conductors from overheating due to excessive current flow. Overheating can damage the insulation of the conductors, leading to short circuits, ground faults, and potentially fires. The code specifies the maximum allowable overcurrent protection for different conductor sizes and types, ensuring that the protection device will trip or open the circuit before the conductors reach a dangerous temperature. Article 240.21b6, titled Transformer Secondary Conductors, provides an exception to the general rule of overcurrent protection at the source for transformer secondary conductors. This exception, often referred to as the 25-foot tap rule, allows for a limited length of unprotected secondary conductors under certain conditions. The rationale behind this exception is that in some cases, it may be impractical or unnecessary to provide overcurrent protection at the transformer secondary terminals, especially for short runs to specific loads. However, this exception comes with strict requirements to ensure safety. Firstly, the length of the secondary conductors must not exceed 25 feet. Secondly, the ampacity of the secondary conductors must be at least 1/3 of the overcurrent device protecting the primary of the transformer. Thirdly, the secondary conductors must terminate in a single overcurrent device or a set of overcurrent devices that limit the load to the ampacity of the conductors. Fourthly, the overcurrent device on the secondary side must be readily accessible. Fifthly, the secondary conductors must not be in contact with combustible materials. Sixthly, the secondary conductors are suitably protected from physical damage. In the scenario described, the conductors run from the transformer secondary to a main distribution board, which is not considered a single load. A main distribution board feeds multiple loads, and therefore the exemption in Article 240.21b6 does not apply. The conductors are in violation of Article 230.7 because they lack overcurrent protection at the transformer secondary, which is their source. The contractor's argument that the pole boxes and wireway provide sufficient physical protection is not valid in this case. While these enclosures offer some level of protection against physical damage, they do not provide overcurrent protection. Overcurrent protection devices are specifically designed to interrupt the circuit in the event of an overcurrent, preventing overheating and potential fires. A lack of overcurrent protection at the source poses a significant safety hazard. In the event of a short circuit or ground fault on the secondary side of the distribution board, the unprotected conductors could be subjected to extremely high currents, leading to rapid overheating and potential failure. This could result in a fire or explosion, endangering personnel and property. To rectify the situation, it is necessary to install overcurrent protection devices at the transformer secondary terminals. These devices should be sized appropriately to protect the conductors based on their ampacity and the expected load. Alternatively, the secondary conductors could be rerouted to comply with the requirements of Article 240.21b6 if feasible. This would involve ensuring that the conductors are no more than 25 feet in length, have an ampacity of at least one-third of the primary overcurrent device, and terminate in a single overcurrent device or a set of overcurrent devices that limit the load to the ampacity of the conductors. In addition to addressing the overcurrent protection issue, it is also advisable to review the installation practices within the pullboxes and wireway. The code requires that conductors of different systems be physically separated to prevent accidental contact and potential hazards. If it is not possible to maintain an adequate separation between the transformer secondary conductors and other feeder cables within the pullboxes, it may be necessary to install barriers or dividers to provide the required separation. In summary, the installation described is in violation of the National Electrical Code due to the lack of overcurrent protection for the transformer secondary conductors. It is crucial to address this issue promptly to ensure the safety of the electrical system and prevent potential hazards. The recommendations provided, including the installation of overcurrent protection devices and the review of wiring practices, will help to bring the installation into compliance with the code and provide a safe and reliable electrical system. Let's consider the specific parameters of the scenario. We have a 750 kV amps dry-type transformer with a 12.47 kV primary and a 120/208 volt secondary. The secondary conductors run less than 25 feet to a 2500 amps main distribution board with a bolted pressure switch main. Because the conductors are less than 25 feet, the 25-foot tap rule is immediately called into question. We also know that these conductors do not have overcurrent protection at the source, which is the secondary side of the transformer. The existing large pullboxes at the ceiling of the room contain other feeder cables, and there is no physical separation between the transformer secondary conductors and the other feeder cables. Given these specific parameters, let's reiterate the code violations. Firstly, the conductors are in violation of NEC Article 230.7, which requires that feeders be protected from overcurrent at their source. These secondary conductors do not have overcurrent protection at the transformer secondary. Secondly, while the 25-foot tap rule in NEC Article 240.21b6 might seem applicable at first glance, it is not. This is because the conductors terminate in a main distribution board, not a single overcurrent device or a set of overcurrent devices that limit the load to the ampacity of the conductors. The main distribution board feeds multiple loads, disqualifying it from the tap rule exception. Thirdly, the lack of physical separation between the transformer secondary conductors and other feeder cables in the pullboxes may also constitute a code violation, depending on the specific requirements for separation in the applicable code articles. Now let's discuss the potential solutions in more detail. The primary solution is to install overcurrent protection devices at the transformer secondary terminals. The size and type of these devices should be carefully selected based on the ampacity of the secondary conductors and the expected load on the distribution board. It is crucial to consult with a qualified electrical engineer or contractor to ensure that the overcurrent protection devices are properly sized and installed. Another possible solution is to reroute the secondary conductors to comply with the 25-foot tap rule. This would involve ensuring that the conductors are no more than 25 feet in length, have an ampacity of at least one-third of the primary overcurrent device, and terminate in a single overcurrent device or a set of overcurrent devices that limit the load to the ampacity of the conductors. However, this solution may not be practical or feasible in all situations, depending on the physical layout of the installation and the available space. Regarding the issue of physical separation in the pillboxes, there are several possible solutions. One option is to install barriers or dividers within the pillboxes to provide physical separation between the transformer secondary conductors and the other feeder cables. Another option is to reroute the conductors to provide the required separation. If neither of these options is feasible, it may be necessary to replace the existing pillboxes with larger ones that can accommodate the required separation. It is important to note that all electrical work should be performed by qualified and licensed electricians in accordance with all applicable codes and regulations. Improperly installed electrical systems can pose serious safety hazards, including electric shock, fire, and explosion. Now let us focus on the applicable NEC sections. NEC 230.7 addresses overcurrent protection for service entrance conductors and feeders, mandating protection against overcurrent at the source. Overcurrent situations include overload, short circuits, and ground faults. Overload refers to an operation of equipment in excess of normal full load rating, which, when it persists for a sufficient length of time, would cause damage or overheating. Short circuit is an abnormal connection of relatively low impedance between 2 points of different potential. Ground fault is an unintentional electrical path between a source of voltage and ground. Article 240.21b6 addresses the tap rule. This section outlines specific conditions under which conductors can be tapped from a feeder or transformer secondary without overcurrent protection at the tap point. One key requirement is the 25-foot length limitation. Another key element is the 1/3 ampacity rule that says the tap conductors must have an ampacity not less than 1/3 of the overcurrent device protecting the feeder conductors from which they are tapped. These tap rules exist to balance practical installation considerations with safety requirements. However, it's crucial to understand the limitations and ensure all conditions are met when applying these rules. When the tap rule is not met, the conductors must have overcurrent protection at the point they receive their supply. The goal is always to protect conductors from overcurrent conditions to prevent overheating and potential fires. Now consider conductor ampacity. The ampacity of a conductor is its current carrying capacity in amps. This value is determined by the conductor material, size, insulation type, and installation conditions. The NEC provides tables that list the ampacities of various conductors under different conditions. When selecting conductors for an installation, it is critical to choose conductors with an ampacity sufficient to carry the expected load. The overcurrent protection device protecting the conductor should be sized no larger than the conductor's ampacity. The NEC also provides guidance on correcting conductor ampacity for ambient temperature and the number of conductors in a raceway or cable. These correction factors must be applied to ensure that the conductors can safely carry the intended load. Next, let us discuss physical protection and separation. While overcurrent protection is the primary means of protecting conductors from overcurrent conditions, physical protection and separation are also important considerations. Conductors should be installed in a manner that protects them from physical damage, such as abrasion, impact, and exposure to corrosive substances. This can be achieved by using appropriate raceways, such as conduit or tubing, or by installing the conductors in areas where they are not likely to be damaged. Separation of conductors from other systems, such as communication cables or piping, is also important to prevent accidental contact and potential hazards. The NEC provides specific requirements for the separation of conductors from other systems, depending on the voltage and type of conductors involved. In the case of the pillboxes, the NEC requires that conductors of different systems be physically separated to prevent accidental contact and potential hazards. This can be achieved by using barriers or dividers within the pillboxes, or by rerouting the conductors to provide the required separation. Now consider the role of a qualified electrical professional. Electrical installations can be complex and hazardous. It's crucial to involve a qualified electrical professional to design, install, and inspect electrical systems. A qualified electrical professional has the knowledge, skills, and experience to ensure that the installation complies with all applicable codes and regulations and that it is safe and reliable. They can properly size conductors and overcurrent protection, ensure adequate physical protection and separation, and perform thorough testing and inspections. In the scenario discussed, the contractor, despite doing good work in bundling cables, still failed to meet code requirements, highlighting the importance of proper code knowledge and application. Let's further consider the transformer. Transformers are essential components in electrical power distribution systems. They are used to step up or step down voltage levels to match the requirements of different loads and equipment. Transformers consist of 2 or more coils of wire wound around a common core. The primary winding is connected to the source voltage, and the secondary winding is connected to the load. The ratio of the number of turns in the primary and secondary windings determines the voltage transformation ratio. Transformers are typically rated in kilovolt amps, which is a measure of their apparent power capacity. The kilovolt amps rating indicates the amount of power that the transformer can deliver without exceeding its temperature limits. Dry-type transformers, like the one in this scenario, are cooled by natural air convection. They are typically used indoors in commercial and industrial applications. Dry-type transformers are generally considered to be safer than liquid-filled transformers, as they do not pose a risk of oil leakage or fire. The transformer in this scenario has a 750 kV amps rating, a 12.47 kV primary voltage, and a 120/208 volts secondary voltage. This means that it can deliver up to 750 kV amps of power at a secondary voltage of 120/208 volts. The primary voltage of 12.47 kV is a common distribution voltage in many areas.